Good morning. Hopefully everyone's doing good. In the last class, we talked about frequency response, and we saw that a filter or a linear time invariant system can change the input frequencies, changing their amplitude and changing their phase. We're going to look more in detail in this class at the phase, what we call phase and group delay. Now, as I mentioned, the frequency response is h of e to the j omega. We can write it as magnitude and phase. And of course, what we write as theta of omega is going to be the difference in phase between the input and output. It tells us how much delay there is between a signal when it enters and when it goes through the filter. Now, we know from before that if the input is a cosine, the output is going to be a cosine with the same frequency. The only thing is the amplitude is going to change and the phase is going to change. So theta of omega 0 is going to be the difference in radians. Now, what does that mean? Right, a change in amplitude, we can think about it and it's kind of easy to understand, right? It just makes it bigger or smaller, or it might leave it the same. But what does a change in phase do? Well, actually, it means that the input cosine and the output cosine, in this case, are going to be, one is going to be shifted relative to the other. One is going to be ahead. And that's what the phase is going to tell us. And it tells us what is that offset, or what is the difference in radians. Now, that's nice, but it doesn't tell us as much as if we had the difference in samples. Right, if they tell us the difference is 2 radians, well, we go, okay. But if they tell us the difference between the input and the output is 3 samples, ooh, that is something that's reasonable and is easily used. So how do we change from having the difference in phase to having the difference in samples? Well, let's look at it. Let's go back to the same filter we had before. As we know, the frequency response for that filter we already calculated, and was this. And this was our phase. Now let's look at it for the 2 cosines that we put through the filter. Right, the phase here is going to be minus 0.2, and the phase for the other cosine is going to be minus 2. Now, the difference in phase in the first cosine is going to be 0.2 radians. But how much is this in samples? Well, these 2 cosines have a frequency of 0.2 radians per sample. So a difference of 0.2 radians is going to be a delay of 1 sample. Right? 0.2 radians divided by 0.2 radians per sample, which is the frequency, gives us the differences in samples. We can do the same thing for the second example, right? The difference between these cosines is 2 radians. Since they have a frequency of 2 radians per sample, the delay is going to be, right, 2 radians divided by 2 radians per sample. Again, the difference is going to be 1 sample. If you go back and look at the examples of the cosines, you can see that actually there is a delay of 1 sample between the input and the output. Now, how do we do it in general? We don't want to go and have to calculate this for every frequency. What we do is we calculate what we call the group delay. If theta is our phase difference, right, this is the phase of the filter. The group delay, in other words, how many samples the filter is going to delay the signal when it passes through the system, we're going to call it tau. And it's just the derivative of the frequency with respect to omega. We take the negative because we're talking about the delay. And of course, this is going to give us samples. In the example above, right, the filter we had before, the phase was minus omega, so the group delay is just 1. As we saw in the example which we just showed, the delay in samples is going to be 1 sample. Right? In other words, this filter is going to have a delay of 1 sample for all frequencies. Now, that's nice. It means no matter what frequency I put in, the time it takes to go through the filter is going to be one sample. Now this is nice because many times we don't just put in one frequency to a filter, we can put in many frequencies. And it means that if we put in two frequencies at the same time, they're going to go through and come out the filter at the same time. We can have filters that don't have this uniform delay. In other words, we can have a filter that two frequencies going together, but one comes out before the other. Now, filters that do have this property, that have the property that the delay is the same for all frequencies, are going to be called linear phase filters. Now, as in this case, we saw theta is a linear function of omega, and so that's why we call them linear phase filters. Now let's look at another example before we go on and talk specifically about linear phase filters. Let's look at this filter here. Right, we can easily calculate its DTFT, and so we can calculate its phase. Again, if we write this is going to be the real part, this is going to be the imaginary part. So the phase is just going to be the phase of the numerator minus the phase of the denominator. The phase of the numerator is 0. So the phase of the denominator is going to be the inverse tangent of the imaginary part divided by the real part. So it's minus the inverse tangent of this. Now if we calculate the group delay, right, minus the derivative of the phase with respect to omega, we get this long thing here. Right? The problem is we're taking the derivative of the inverse tangent, and so it comes out rather messy. And we can get this function here. We can see that this does not look like a linear function. In other words, if we change omega, the group delay is going to be different. Right? So the group delay is going to change with the frequency. Again, so for some frequencies, the delay might be 5 samples. For other frequencies, it must be 10 samples, and so forth.